Let's talk about vectors. Vectors are used to describe often forces, and we are interested in both the position of that force and also the strength of that force. And so a vector has both a magnitude and a direction. And as we look at vectors, vectors are equal if they have the same direction and the same magnitude. Now you should have learned something about vectors in the past, and this will review that, but then we're going to add to that. Now, if we looked at the blue vector and the orange vector, these vectors have the same magnitude. They are the same length, but they have a different direction. If we looked at the blue vector and the green vector, these vectors have a different magnitude. You can see they're different lengths here, but they have the same direction, because if I measured off from the horizontal and I measured this angle, it is the same. So these have the same direction, but they have different magnitudes. Now, if we looked at the blue and the purple, these are equal vectors. They look like they're in different places here, but they have the same length or magnitude, and they have the same position or angle. So blue and purple are equal vectors. Now, as we look at a vector, a few things about those. They have an initial point and a terminal point, and then the magnitude is the length, and then measuring off the horizontal we have the direction, which would be that angle right there. Now, if we wanted to know the magnitude and the direction, we could turn this into a right triangle, and then you can see we could just use the distance formula or the Pythagorean theorem, which the distance formula is based on, to find the magnitude or the length of the vector. We could also use what we've learned about trig and right triangles to find this angle, because this would be tangent theta would be opposite over adjacent, and so the angle would be the inverse tangent of opposite, which would be y2 minus y1 over adjacent x2 minus x1. It's easiest to find a vector if we have the initial point be at the origin. So if we have this vector PQ at some x1, y1 and x2, y2, we could actually subtract these two x's and these two y's, and we could convert this to what we call a position vector. And so it would have an initial point at 0, 0, and then some x, y for the terminal point. So it's called a position vector when we do this, would make it convert it to have its initial point be at 0, 0. Now when we add vectors, we put the tip of the first vector to the tail of the second vector. So we would move this over because we have an equivalent vector. They're equal as long as they have the same magnitude and direction. And then the sum would be where we started, the initial point, and where we ended up, the terminal point of W. So this is the sum right here. The notation for a position vector, then, we put these little brackets on them, and then we know that that one has an initial point at 0, 0 and a terminal point of A1, A2. We put bold letters to designate vectors. So if we looked at this vector, we would plot that point A1, A2, and then we would draw a vector originating from the origin and ending at the A1, A2. Now, if we look at a vector that is 1 unit long in the x direction, that is called a unit vector. And we could look at one in the y direction, and we could figure out then how to express this position vector in terms of these unit vectors. And so we could express that as we would move over A1i and A2j. We'd add those in, and we would have another way to express the vector, just two different notations for vectors. So for example, if we had the vector 3, 2, we could plot that by plotting the point 3, 2, and then we could figure out that it's 3 i's and 2 j's, and so here is another way to express that same vector. So if we looked at a vector and we wanted to look at the negative of that vector, the negative is just a vector going the opposite direction. And so we could easily express that, and we would just need to keep it the same length, but have it starting where the tip of this was and ending where the initial point of this was. Now, if we want to multiply a vector by what is called a scalar. So we're going to look at real valued scalars here. So if we multiply it by a real number, it means to take the vector and add it together that many times. So if we wanted 3v, we would just take 3 times v. So we would take v plus v plus v. And there is our vector, starts here and ends here. There is 3v. So we can add vectors here. Let's try some. So if we wanted negative 3w, we would take our w vector, make it go the opposite direction, and put 3 of them. So 1, 2, 3 in the negative direction, there's 3w. If we wanted u plus v, remember we take u and we put v's tail on the tip of u, and then where we started to where we stopped is our u plus v. So the purple vector there is u plus v. If we wanted u minus v, we would take u, but we would put v on the end, but we would have it go the opposite direction because of the negative on the v, and then where we started to where we stopped, there is u minus v. So if we had several of these operations, we just simply do that. So we're going to take 2u, and then on the tip of that, we are going to add on 3w. And then on the tip of that, we are going to add on v. And then where we started to where we stopped is 2u plus 3w plus v. So when we add vectors and we're not going to draw them every time, we are simply going to combine those. So we're going to put those here. And when we combine those, we have negative 2i plus 3i, and so that would give us I, and we have a 5j minus a 4j, that would give us the j. If we looked at this graphically then, here's our negative 2i plus 5j, and so there's our first vector. And then if we add on w, we do our 3 and minus 4j, and then our resultant vector is where we started to where we stopped, and that is our ij. Now if we wanted to know the magnitude of v, the magnitude would be the length, and remember we saw we could do that based on the Pythagorean theorem, so we could look here and to get this length right here. So that would be this negative 2 squared plus 5 squared, and square rooted would give us that length, and so that would be the square root of 29. Now we can do all of this in 3 space. So if we're looking at R3, our vectors will be bold. Here's our notation, but we will have a third component, z, here. And so we could have our PQ here, same way. And we could generalize this to any space. So if we had an n-dimensional space, we would have n components to our vector, and we could use the same operations and work this the same way. So let's go ahead and look here in R3. So we would have our unit vector I in the x direction, j in the y direction, and then we're going to have k in the z direction. They're 1 unit long. We could express vectors also in this ijk notation then. So if we have this vector whose initial point is the origin and its terminal point is P here, we could also express that as the vector from O to P, and put a little line over it so we know it's the vector, and we could express it as ijk notation or as our position vector notation here. Okay, so what if we had vector PQ in 3 space here? So let's go ahead and plot the 2 points, and then we could draw the vector. So for vector P, we are going to have 1 in the x direction, 2 in the y direction, 3 in the z direction. So there's point P. Then 4. So there's point P. Then we're going to go 4 in the x direction, 1 in the y direction, and 4 in the z direction, and there's point Q. So our vector PQ starts at P, goes over here to Q. Now we could take this vector and we could make it a position vector by putting its initial point Q, transforming that down to the origin, and then it would look like this. we could express that vector. This is the vector 3, negative 1, 1. We could find that by taking the components. 4 minus 1 is 3, 1 minus 2 is minus 1, 4 minus 3 is 1. And you can see that's the case here, because if we went out 1, 2, 3, and we did negative 1 in the y direction, and then we did 1 in the z direction, we would end right there. So if we have a vector and we want its magnitude or its length, we use the distance formula essentially. Well, if in 3 space we can do the same thing. We have a 3-component vector, so if we want its magnitude, we can apply again the distance formula. And if we have it in component form, since the second point is the origin, it's a1 minus 0 squared essentially, so we don't need to put that. So plus a2 squared plus a sub 3 squared, square rooted. So properties of vectors, if we have these vectors and we have C and D that are scalars, these properties are true about them, and they're fairly easy to see. We're going to look at a couple of them geometrically to see that, but they'd be fairly easy to prove if we just think about the properties of vectors. So let's look at the first one. It just says they are commutative when you add. This one says under addition they are associative. You could add 2 of these first and then the third one, and it doesn't matter which 2 you add first. This one says if you add the 0 vector to it, you get the vector back, and that would make sense because we're adding components. So if we're adding 0 to each component, we're still going to have the same vector. This one says if you add the opposite, you'll get the 0 vector. Notice these are bold because these are vectors of zeros. They're not just the number 0, but they are vectors that have 0 for each component. This one says that if you have a scalar, it distributes to the vectors, and it also, if you have 2 scalars, it will distribute as well. And this one says it is associative with multiplication of scalars, and this one says if you multiply by the scalar 1, you will get the vector back again. So they're all fairly obvious. Let's look at the first 2 and see those geometrically. So if we took 2 vectors and we figured out v plus w, it would look like that. What if we turned it around or commuted it and we did w first and then we put v on the end? You can see that we would arrive at the same place. You can see it geometrically, but it also makes sense because we add components and we know that addition of real numbers is commutative. Now looking at this associative property, if we did a plus b, and so we'll put those together first, and there is a plus b, and then we added on c. Here is our resultant vector pq. Well, what if we did it that we took a, so that would be this purple a, and then we added on to a b plus c. Well, here's b plus c right here, so there is the vector b plus c, and you can see that if we did this a and then b plus c, that we again get pq. So remember, a unit vector is a vector of magnitude 1. So if we started with this vector in 3 space, and first of all, if we want to know its magnitude, we can take each of the components squared and add those together and then square root them, and we get the square root of 29. If we wanted to get a unit vector in the direction of w, then we could take w and we could divide each of these components by the square root of 29, and this would give us a vector in the direction of w that was a unit vector. If you figured out the magnitude of this vector, it's 1. Now, vectors are used often to explain forces and to look at kind of directions of the resultant force. So if we had this airplane moving along and it has a certain velocity relative to the air, so what the engines are pushing it and so forth, but it has a wind blowing, so it's facing this wind, and this wind is blowing in this direction, and so the resultant, if you're looking on the ground, seeing the position relative to the ground of how the plane is moving, it would be the sum of the two. So the velocity relative to the ground would be the velocity that the airplane is actually going based on its engines and so forth, plus the wind, and then we have our resultant vector. So we will use vectors, and we'll see some examples of these, of how we can look at various forces being combined and our resultant force.